Okay, functions. I'm going to be a bit informal, and I'll just keep providing you with examples for these functions. The first, what's a function? Definition. A function takes in an input and gives you back an output in a consistent way meaning that you get same output for same input. In other words, it's like a machine where you plug in something and it gives you back something. It doesn't necessarily have to be numbers, but in our class it will mainly be where you plug in numbers, you get numbers back. So it's like a machine where if you plug in 2 as the input, it will give you some other value, say 5. Now, if you plug in 2 again and it gives you a different number this time, that's not a function. Okay? If it gave you 5 once, then it should always give you the same value. All right. Now, as an example, example 1, think about the following. F of x equals x squared. That's a function because if you plug in 3, what do you get as the output?
9.
9. And 3 will always give you 9, right? You don't get a different value. That's an example of a function. Okay. Here's another example. Say you have y plus x squared equal to 0. Now this equation makes this defines y as a function of x. If you provide a value for x, this relationship defines y as a function of x, because what will be the value of x if you have x equals to 3? What do you get? Y plus 9 equals to 0, so y is negative 9. So here's an example where for every value of x, you get a value of y. So now let me give you an example where it's not a function. So example 3. Suppose you have y squared minus x equals to 0. So this case does not define y as a function of x. So here, y is not a function of x because, let's think about the following case. What if x is 9? What do you get? You get y squared minus 9 equal to 0, right? And you get y squared equals to 9, so y must be 3, or negative 3. So you could have y as 3 to satisfy this equation, or also negative 3 to satisfy this equation. So both 3 and negative 3 are possible outcomes, but functions should only give you one specific outcome repeatedly. You can't have 3 one time when you plug in 9 and negative 3 another time when you plug in 9. So that's not allowed. Alright? So that's why this is not a function. These examples immediately will remind you of the vertical line test. So I'm kind of assuming that you've seen such a thing before. So let's talk about vertical line test. Vertical line test. Sometimes just abbreviated as VLT. If you drew the graph of y plus x squared equals 0, which is a function, well, if you solve for y, here's how it looks. Y equals to negative x squared. Well, y equals x squared is like a graph that's like that, right? But if you have a minus, it flips upside down, and the graph that you get is an upside down parabola, a parabola that opens down. So that's the graph of example 2, which was a function, which did define y as a function of x. Okay. On the other hand, if you draw the graph y squared minus x equals to 0, then you have y squared equals to x, which if you solve for y, you get y equals to plus or minus square root of x. Right? You take away the square, you get the square root on the other side, but make sure you remember that there should be a plus and minus. Okay. All right. Now once you have this, let's draw the graph of y equals to plus square root of x. And you can do that by just carefully taking y equals to square root of x and plugging in some square numbers. So if you plug in 0, square root of 0 is 0, right? If you plug in 1, square root of 1 is 1, so it passes through 1, 1. If you plug in 4, square root of 4 is 2, so 1, 2, 3, 4. It gives you 2. So the graph is something like this. And keep plugging in more numbers to see that the graph looks somewhat like this. And then if you think about the one that has y equals to negative square root of x, that will be same as this one, but it will be flipped upside down, just like here. So you get the graph looks like here. Which means that if you drew the original graph, it's these two together. Okay? So this will have a graph of both. That will be the graph of y squared equal to x. Is that okay?
Yes.
All right. And now we can try to draw the vertical lines. So if you draw any vertical line, in the first graph where y is a function of x, you see that the vertical line, if it meets at most once. Okay? So here I might say vertical line meets, so any vertical line meets the graph at most once. So that's one possibility. Another case, in the second case, if you draw a vertical line, it meets the graph more than once, right? Now, there are vertical lines that you can draw over here which doesn't meet the line at all. But it doesn't matter. If you have just one vertical line that meets the graph more than once, then you say it fails the vertical line test. Okay, so here there is some vertical line meets more than once, meets the graph more than once. It could be once, it could be twice or three times. I don't care. If it's more than once, and if such a vertical line exists, if one such vertical line exists, then we immediately say that the graph fails the vertical line test. So over here, this is a pass. Over here, it's a fail. Failing the vertical line test means that y is not a function of x. Okay? That's what vertical line tests do. And you can kind of make an argument why it is so. So remember, every point on the plane is made of an x-coordinate and a y-coordinate, right? So having this point on this equation means that when you have an x input, you get that value as the y output. But look, you have this as the y output, and then this also has the y as output. You have two different values for a single input here. That violates our principle of being a function, where a function should only have one consistent output for an input. Okay? Over here, you only have one output, right, for every input, so it's a function. So passing the vertical line test means that it's a function, whereas failing the vertical line test means y is not a function of x. Now we do have to be a little careful. This equation, however, does define x as a function of y. If you think of y as the input and x as the output, then indeed it gives you one output, one consistent output for every input, so it's a function in that case. So y, x could be a function of y, but y is not a function of x. Now, once I start digging deep into x being a function of y, it becomes more confusing, so I'll just stop here and not talk about what it means there, but I just want to make sure that the vertical line test, failing the vertical line test means that y is not a function of x. And it doesn't say what's happening to x being a function of y. That's a different question. Okay, let's talk about domain and range of a function. When you're given a function, the set of all possible inputs to that function is called the domain, and all the possible outcomes is called the range. Here's an example. Find the domain and range of f of x equals the square root of x. Functions like a machine where you put in something and it gives you something back, right? And you know, like some machines can't process certain inputs. Like, let's say, think about a copier which cannot accept papers that are too thick. You can think something like that, right? So that's what range of a function does. It only takes in certain inputs, and collection of all possible inputs is your range. Collection of all possible inputs is your domain. Okay. So let's think about the domain of square root of x. And it's easier to think about what's not allowed into this function rather than to think about what's allowed. So square root of x, what's not allowed to be plugged in into the square root? Do you have any idea? what are you not supposed to plug inside the square root?
-1.
-1, right? Well, technically you could plug in -1 and define the square root of -1 as an imaginary number. But in this class, in a pre-calculus class, when we talk about functions, we'll always agree that functions are real valued. Okay, so when you have an imaginary output, you don't consider it as a legit output. Okay, that's our tacit agreement. Of course, you can talk about functions that will give you complex numbers as output, but that will be some harder mathematics that goes beyond what we can cover here. Okay, so in this class, even if I don't say it, all functions should be real valued outputs. Real valued functions. So -1 is not okay, or negative anything is not okay. Square root of a negative number gives you a complex number. We don't deal with those kind of functions. Okay, now what about 0? Can you plug in 0 into the square root? What do you think? How many of you think 0 is okay inside the square root? How many of you think you can't plug in 0 inside the square root? Okay. What is the square root of 0?
No.
Nothing.
Undefined.
0.
It is 0 because, look. See, 2 squared is 4. Then we say square root of 4 is 2, right? So 0 squared is what? 0. So we say square root of 0 is 0. That's how we say it, right? Now the question is, so can we plug in 0? Do we have an output that's legit? Yes. 0 is a real number, so it's okay. So into the square root, 0 could be plugged in, because square root of 0 is defined. It's a different thing to say that the output is nothing and to say that the output is 0. 0 is a number, whereas since square root of -1 is not allowed, this is not an output. Okay? This is a legit output. So 0 is okay, and any positive number is okay, right? What output do you get if you plug in 2? What's square root of 2? Well, it's not an integer, but there is such a number. Square root of 2 is about 1.414213, right? So you get something called the irrational number, but those numbers do exist. Okay, so after thinking about what's possible to be plugged into this machine without breaking the machine, we see that anything that's positive is okay, 0 is okay. Right? So we say x must be 0 or above for the input. Okay? Now how do you write this as an interval notation? In interval notation, how do you write this? Yes?
Bracket 0.
Bracket 0 to
Infinity. Parentheses.
infinity, and then parentheses, right? And we use the bracket because this closed bracket means 0 is included in the domain. 0 is allowed. Okay, so that's your domain. Now, what about the range? Well, range is a bit harder to argue for, but if you think about anything squared, as long as a is 0 or positive, then square root of a squared gives you a, right? Right, just as square root of 4 is square root of 2 squared, and then 2n squared cancels to give you 2, right? So, I mean, we know all kinds of identities that's like this. Square and squares cancel. So, because of this, we see that any number could be the output of this function. Right? If I want 1,000,000, what do I plug in here? 1,000,000 squared. Okay? If I want 121, what do I put in here? 121 squared. And then it gives you the output that I desire. Any number could be the output. So because of that, we see that the range is also 0 to infinity. Oh, by the way, square roots by definition never gives you back a negative number, right? So I know that negative 3 squared gives you 9 as well, but we don't say square root of 9 is negative 3. We say it's positive 3. Okay, because by definition of the square root, we forbid it from ever spitting out a negative number. Okay? Although both negative 3 and positive 3 squared to 9, we only make it give you positive 3. Okay, so because of that, the range is never negative. Now, however, this kind of argument for finding range is quite confusing. So, in most of the cases in this class, we'll be using the graph of the function to determine its range. Okay? And let me explain what I mean by that. So, a moment ago, we drew the graph of y equals the square root of x. Let me quickly do it here again. So x, y, if you have 0, 1, 4, and maybe 9. So what's square root of 0? 0. Square root of 1? 1. Square root of 4? 2. Square root of 9? 3. So you draw this. And then 0, 0, 1, 1, and then 4, 2. Here's 9, 3. So you have that as the graph. Okay? So that's the graph of y equals the square root of x. And from there we can read the domain and range. First of all, for any point on this graph, there's a pair of x values and the y values, right? And what it means is that if you plug in this value, you get that as the output. So this is about 7. Square root of 7 is it's 2.4 something. So it's about 2.4. You get that as the output. Which means that if you collect all the x values, that's like going through every point on this graph and drawing a straight line to the x-axis and seeing what their x-coordinates are. And as you can see over here, every value on the x-axis on the right side have something, right? Including 0. Whereas you don't have anything from the left side, and immediately you see that the domain of this graph is 0 to infinity, just like what we saw here. Another way to visualize this is just imagine that there's a light source way up there. And then that light source is shining upon this graph, and there's a shadow on the x-axis. Then the shadow only is from here up to infinity, right? So that's going to be your domain. That's another way to think about it. In the same way, for every point on the graph, we can look at its y value by drawing a horizontal line towards the y-axis. Then we see that, again, all the y values all the y values are targeted from some point, right? Another way to say it is like there's a light source in the positive infinity on the right side, shining in this way, and there's a wall, and you're looking at the shadow on the wall, and it's from 0 to infinity. So that's how you can read off the range. Is this okay? All right, so if you're convinced with this this reading of the graph, let me give you a slightly challenging example. So, example 2, find the domain and range of y equals the square root of x minus 2 plus 5. Let's think about that. First of all, determining domain doesn't really require you to look at the graph. It's kind of straightforward. So you have a square root. What do you know about square roots? They can't accept negative numbers. So the thing that's inside the square root, which is x minus 2, must be 0 or positive, right? It has to be 0 or positive. And therefore, if you add 2 both sides and solve, what do you get? You see that x must be 2 or greater. So if you plug in something that's less than 2, then it will cause a problem. For example, if you plug in 0, you get square root of negative 2, which is a complex number. We don't allow complex output, so that's not a valid output. So 0 is not supposed to be plugged into this function. Neither is 1. But 2 is okay. If you plug in 2, 2 minus 2 is 0, square root of 0 is 0. So it gives you the output of 5 after adding the 5. It's perfectly fine. So we can see the domain starts from 2, and anything after that is okay. 2 to infinity. And because 2 itself is included, you put a square bracket, also known as a closed bracket. That's your domain. But then, trying to think about the range of this is a bit more challenging, so let's just try to graph this and see what the graph tells us. But to graph it, that means we need to know how to graph y equals the square root of x minus 2 plus 5. And instead of trying to draw the graph of this immediately at once, it's better to first think about the graph of y equals the square root of x, which is like this, right? And then you use this to think about the graph of y equals the square root of x minus 2, something. And then later on you use that to draw the graph of y equals the square root of x minus 2 plus 5. That's going to be our plan. Yes?
Are we supposed to know like how to graph it? Like how are you supposed to know like y equals square root of x looks like that? Do we have a calculator for the test or something?
Well, you have to think about this given thing as some kind of transformation applied to this one. See, if you replace x by x minus 2, this is what you get. And if you add 5 to the entire thing, you get what? This is what you get. So you have to think about the effect of going from x to x minus 2, and also the effect of adding a 5 to the function. You have to know how to draw the graph just from this beginning function. Yeah. You have to be able to draw this without the aid of a calculator, right? Okay, so first of all, if you replace x by x minus 2, what's the effect on the graph? What would the graph do? Take a guess. What would the graph? Okay, some people are saying it goes up, some people are saying it goes left. However, remember that the domain is 2 to infinity, right? So the domain is 2 to infinity. We just figured that out, right? 2 to infinity. And so that's like a shadow if you have the light source off from the infinity. So what kind of graph would be having this as a shadow? If you took this graph and moved it which direction? Right by 2, right? So the graph will actually move right by 2. And this is something that always happens. So let me just write that over here as some principle. If x is replaced by x minus 2, the graph moves right by 2. Okay. So that's called translation. The graph is translated 2 to the right. If you subtract, it moves right. If you add, it does the opposite. So if it was square root of x plus 2, then this graph will move left by 2. It does the opposite. That's what replacing does. Is that okay? Now, I could go on and maybe spend 20 or 30 minutes to explain why this happens, but after trying that for my years of teaching, I realized that the explanation of why things work that way is more complicated than the phenomenon itself. So now I just tell the students, well, just go onto any nice online graphing site. Desmos is one. Type this in, SQRTX, and type this in, which is SQRTX minus 2. Observe that it does move 2 steps to the right. And you just do different changes, like instead of x, put x minus 3, x minus 4, put x plus 5. And if you do that, you'll see that every time you do that, the graph will move the opposite direction of what you would expect. So if you add, it moves left. If you subtract, it moves right. Okay? Just simply accept that as like something that you learn out of experiment. Yes?
So if I was to subtract, I'd be plotted, so where the 2 is right now, I'd be plotted at 0 for the negative 2.
I don't quite understand your question. If you plug in 2, what happens? 2 minus 2 is 0.
Yeah.
Square root of 0 is
0.
0. So you have 2 comma 0. Was that your question?
Yeah.
So 0 comma 0
Yep.
was this tip, whereas over here, when you plug in 2, that's the first point where the graph starts.
Okay.
Yeah, so in fact, you can just plug in some values to see that, and try drawing to see that indeed it moves right. Okay? All right, but then think about what would happen from here to there. See, you have, for every x value, it produces the y value. That's what this relationship does, right? But now you're adding 5 to the output. So what's going to happen to the y values? It will increase by 5, which means in terms of the graph, it will move up by 5, right? So what it does is, if this is 2 and this is 5, this point, which is the tip of this graph, is going to move up by 5. Just like that. Okay. So that's the graph. Now from here, do you see that the shadow says the domain is 2 to infinity, which we already knew. Okay. What's the range? What's the range? What's? Look at the y values. You can go up as you want, but how low can it go? 5. You cannot go below 5, right? So what's the range? 5 to infinity. So after drawing the graph, we see that the range is 5 to infinity. Find the domain and range of f of x equals to x squared minus 4x plus 7. Let's figure out the domain first, because that's something that doesn't require you to draw the graph. So let me ask, can you plug in 0? Is it okay? 0 squared is 0. 0 times 4 is 0. So you get an output of 7, so 0 is okay, right? Next, can you plug in negative 1? Is it okay to plug in negative 1 to square it? What do you get if you do that? You get positive 1. Right? So there is a value, right? If you can calculate it, that means it's okay. Just recall in the previous example, we had a square root. You can't calculate square root of negative 1 without using complex numbers, right? So in that case, -1 is a no-no. However, you could calculate square root of 0, so 0 was a domain in our very first example, right? And so in the same way, if you can calculate for -1 squared and give you the value of +1, that means it's okay. So that means the domain is all reals. You can plug in whatever. Domain is all reals, from negative infinity to positive infinity. And in fact, such a function is called a polynomial because you have x to some power with some coefficient. Those things are added together. These types will always have domain negative infinity to infinity. So f of x equals x to the third power, or x to the fifth power plus x to the third power. If you have x to some power with some coefficient in front, those are called polynomials. They have all real numbers as its domain. There's no restriction to what numbers can be plugged in. That's what I'm trying to say. Okay, but to find the range, now you really need to draw the graph. So let's try to draw the graph of y equals to x squared minus 4x plus 7. Now, we will spend a few lectures later to better draw an equation like this one. So don't be alarmed if the technique I'm showing you is something that you haven't seen before. But we will go over some harder examples than this one in a separate lecture. But first, the idea is this. We want to complete the square on the right side. How do you complete the square? What should we do first? We should subtract the 7 both sides, right? And then, because you have minus 4x, x squared minus 4x, if indeed we had some number to complete this as a square, this is going to be what squared? X minus what? Minus 2. Right? This will be x minus 2 squared. And then, if you want this thing to be here, this number must be what? 4, because negative 2 squared is 4, right? So this must be 4. So I want a 4 here. How do I make 4 appear? You add both sides. So 4 should be added both sides. Now what happens then is this right side, if you try to factor it, think about two numbers that multiply to 4 and add to negative 4. Those are negative 2 and negative 2. So this right side factors indeed to x minus 2 squared. You see that? Okay? So the right side can be just replaced by x minus 2 squared, including this 4. So all of these three becomes a single x minus 2 squared. On the other hand, you have 4 minus 7. What's that? Negative 3. Now you move the 3 back to the other side, and you get y equals to x minus 2 squared plus 3. Now, this looks a lot like what we used in the previous example. Instead of x, you have x minus 2, and there's something added. If you have this format, then start with something that wouldn't have minus 2 and plus 3. And start from that graph and try to think of various transformations that would take you to here. Okay. So what would be the prototype function when you don't have any translations? Y equals to what? Y equals to? What's our prototype function? Original function. No, without minus 2, without plus 3. So what do you get? You get
X squared.
X squared. Y equals x squared. We call that the prototype function. And if you make a chart for x and y, you would come up with this graph. But hopefully you just know this. I mean, this graph appears enough times that you should just memorize it. Okay? Y equals x squared gives you this shape, which is called a parabola. Okay? You get the parabola. Now let's think about y equals to x minus 2 squared. What graph does that give you? It makes the graph move which direction? Right by 2, right? So this tip of the graph will now move 1, 2 steps to the right, and you're going to have this as your graph. Okay? Now, what about this plus 3? What would that do? Y equals to x minus 2 squared plus 3 is going to give you 1, 2 steps, and then 1, 2, 3 steps up. It's going to move this graph, whose tip was on the x-axis, now gets elevated by 3. So 1, 2, 3, you get to this point, and now you have this as your output. This as your graph, okay? After shifting up by 3. Okay, so looking at this graph, where this height is 3, what's the range? Range of the function is 3 to infinity, because 3 is the lowest point that it attains, right? Everything afterwards is above 3. All the values of y are attained. You get that? Okay. So therefore, the answer to this is, after drawing the graph, we see that the range should be 3 to infinity. 3 itself is attained, therefore this is the answer. Find the domain and range of f of x equals to 1 over x. Okay, so this time you have a fraction. What's not allowed in a fraction? Denominator cannot be 0, right? So you see that since x is in the denominator, we see that x cannot be 0. And then as long as x is not 0, then everything is okay. You can divide by any positive number, and you can also divide by a negative number. There's nothing stopping you for dividing 1 by negative 2. That gives you negative 1/2. That's totally fine. That's a nice looking real number. So the only requirement is that 0 is a no-no, everything else is fine. That's the domain. Now, oftentimes during the exam, I'm going to ask you to write down the domain, not in this form, but in interval notation. So let's think about that. If you have the real number line, and so on, then the ones that are positive, ones that are positive will be over here. Ones that are negative will be over here. But 0 is not allowed, right? So there's an open circle here. So if you draw the graph of x not equal to 0 on the real number line, this is what you have. You have a hole at 0, everything else is covered. Now our goal is to write this in terms of the interval notation. And when you try to do that, I see that because there's a hole, there are 2 intervals, right? There's an interval here and there's an interval here. What is this interval? How do you express this interval? Where does this interval begin? Negative infinity. It's all the way up from the left, that's negative infinity. And where does it end? 0. And for negative infinity or positive infinity, you always put the open bracket, or the round one. And because 0 is not included, what kind of bracket do we use? The open bracket. It's not included. So that's what we use, because 0 itself is not included. Now let's try to express the second piece of the interval. What is this one? You start from 0 goes to infinity. Now you take the union of the 2. If you have more than one interval, you put union. Okay. So that's how you write down the domain. But then, again, if you want to answer the range, you have to know the graph. In fact, after this lecture, I'll begin with like basic graphs that you must know. There are certain graphs that you must know by heart, and y equals to 1 over x is one of them. And if you plug in 1 over 1 is 1, right? If you plug in 2, it becomes half. If you plug in 1/2, it becomes 2. So you keep plugging in different values of x, you will see that the graph is like that. Also known as an inversely proportional graph. As x becomes smaller and smaller, say if x is like 0.0001, then 1 over 0.0001 gives you 10,000. So as x goes to close to 0 on this side, you get huge values. That's why you have this vertical asymptote on the y-axis. Okay. And then you can also start plugging in negative numbers, and when you plug in negative numbers, dividing a positive by negative gives you negative. So after making a chart of x values, you will see that the graph on the left side will be below the x-axis, just like that. Such a shape is called a hyperbola because you have two curves that don't meet each other and they diverge from one another. And you know, sometimes we say that discussion was hyperbolic. That means like two sides were talking about something, but they never converged. Rather, they like diverted away. They were like talking about totally different things. Hyperbolic discussion. That's this graph. This shape is called hyperbola. But what we are interested in is looking at this graph and looking at the shadow on the x-axis and also on the y-axis, right? First of all, if you looked at the shadow on the x-axis, what do you get? You get all the values on the x-axis except what? 0. 0 is missed because there is nothing here, right? If you start drawing vertical lines towards the x-axis, it will capture everything except 0. That's why you get this as the domain. We already knew that, but we kind of verified to the graph that the domain is all real values except the 0. And you're right. You end up with the same thing for the range. It's all real values except 0, right? Because look, if you drew horizontal lines through to the y-axis, by doing it on this portion, you get all the values on the y-axis. And if you do it on this portion, you get also all the values. Okay, here you get all the values on the y-axis for the positive ones. You get all the values on the y-axis for the negative ones, and it still misses the 0. So you can see that the range does not include 0. Okay, so as we are doing these examples of domain and range, hopefully that gives you some motivation to memorize these graphs by heart. Now let's move on for the harder questions. Find the domains of f of x equals to square root of x plus 2, g of x equals to 1 over x plus 7, and f of x plus g of x. Notice that in this next question, I'm not asking you for the range, because while it's not unreasonable to ask for the range of this function or that function, once you add the two, the graph becomes a lot more complicated, and I'm not going to expect you to be able to draw a graph of the f of x plus gx, because if that was the task given to me, I'll have to make tables, and I'll take quite a long time to draw that. So it's not viable for an exam question. So for such a question where you have a mix of two things added or subtracted or even multiplied, for those, I'll only be asking for the domain rather than domain and range. Okay, so let's think about that. First, f of x. What's not allowed? X plus 2 being a negative value, right? So x plus 2 has to be what? 0 or positive. It can't be negative. It has to be 0 or positive, which means x must be greater or equal to negative 2. So what is the domain? Including negative 2 until infinity. That's the domain for square root of x plus 2. Is that okay? So that's for f of x. Now for the g of x, what's not allowed in the denominator? Negative 7. So you have x plus 7 can't be 0, right? You can't have x as negative 7 for the denominator because negative 7 plus 7 will give you 0. Another way to say it is you can't have x plus 7 as 0. X plus 7 should be non-zero because that's the denominator. And you can solve this non-equality just like how you solve equality. You just subtract 7 both sides and you get x not equals to negative 7 after subtracting 7 both sides. Okay. And that one, if you want to write in interval notation, what's that? Again, you have an entire number line. You take the negative 7 away. Then you have two pieces on the number line, right? Negative infinity up to where? Negative 7. Okay, and then negative 7 to infinity, and then you put the union between the two. Okay? So that's the domain for g of x. Okay, now what about fx plus gx? Well, fx plus gx is square root of x plus 2 plus 1 over x plus 7. And that tells us that we have two requirements. One requirement is that for this to be defined, you need x to be negative 2 or greater, right? Just like here. Now, for this to be defined, what do we need? X plus 7 cannot be 0, so that x cannot be negative 7. And both of these requirements must be satisfied in order for this function to be evaluated. Do you agree? But if you think a little bit more, if x is greater than negative 2, this never happens. So this just comes as automatic. You only need this. So in this case, the domain will be the same thing as f of x, negative 2 to infinity. Do you have a question here? If not, let's move on to the next question. Very similar to what we just did. Example 6. This time, it will be exactly same as before, but instead of plus 7, I'm going to put minus 7. Okay? Now, because we didn't change f of x, this answer is the same, right? How would this one change? G of x. This time x minus 7 cannot be 0, so x cannot be what? Just add 7 both sides, right? So x cannot be 7. And therefore, the domain is negative infinity up to 7, union 7 to infinity. Okay? So that part is not that surprising, but here's where there's a big difference between this example and the previous one. So if we add the two, we have this as the function, and this part requires that x has to be negative 2 or greater. This part, we just determined that x cannot be 7. And the problem is, this time just being greater than -2 doesn't prohibit x being 7. This could happen even if this is met. Okay? So in order to see what's the condition for both of these to be met, you should draw the number line and try to graph this situation where this is true and this is true. Okay? So first of all, here's -2, here's 7. And the above condition is saying that as long as it's -2 and above, it's good. Oh, but wait, 7 is no good, right? So that has to be skipped. This should be an open circle. And after 7, that's good. So this is the domain. Does this make sense? For these two to both work, you need it to be more than -2, including -2. But 7 should be deleted because that 7 is going to be a troublemaker when you plug in over here. 1/7 minus 7 will be 0. 1/0, you're not supposed to divide by 0. Okay? So that's the domain. Now if you're fully convinced of this explanation, the next task is to figure out what this is in terms of the interval notation. First of all, how many intervals do you see? I see one piece. I see another piece, right? 2 interval pieces. Okay, tell me what this first piece is. It starts at -2, it ends at 7. Okay, -2 and 7. Now for the -2, should I use closed bracket or open?
Close.
Closed, because it includes -2, so I put closed. How about here?
Open.
7 should be open. It's a round bracket because 7 should be skipped. 7 is a no-no. You can't plug in. Okay? So that's one piece. Okay, what's the other piece? This one. Starts at 7, right? Goes to infinity, and both open because 7 is not included. Infinity is always not included. Infinity is not a real number. Okay, and then if you have more than one interval, what do? You put a union. Okay? So that's the answer to this question.